So hey guys, you've learned about the alkanes with single bonds, the alkenes with double bonds, and the alkynes with triple bonds between their carbon atoms. Let's learn about a special class of organic compounds, the aromatic hydrocarbons. Aromatic hydrocarbons are a special class of compounds because they exhibit several interesting characteristics. Let's commence our study of the aromatic hydrocarbons with benzene, one of the earliest known aromatic compound and the parent molecule for most other aromatic compounds. When Michael Faraday heated whale oil in 1825, he isolated an interesting sweet-smelling compound which was later named benzene. Benzene was found to have a very interesting molecular formula, C6H6. This molecular formula did not fit into any of the widely known molecular formulae for hydrocarbons. It did not fit into the general molecular formula for alkanes, neither did it fit into that for alkenes nor alkynes. So, for a long time, the structure of benzene puzzled several chemists because, though highly unsaturated, benzene was unusually unreactive towards reactions that were common to unsaturated alkenes. For instance, early chemists discovered that benzene remained unreactive in bromine water, even though alkenes reacted with bromine water. After several investigations, a German chemist, August Kekule, suggested in 1865 that the compound benzene had not a single structure, but two structures which rapidly switch between themselves. That is, they are in rapid equilibrium. These structures were called the Kekule structures of benzene, and they are cyclic. That is, the carbon atoms are bonded to one another to form a cyclic structure. There was one more thing though. Kekule structures had alternating single and double bonds. The double bonds were slightly shorter than the single bonds in his cyclic structures. And this held on for a while until the early 1900s, when results from X-ray diffraction studies on this unusual compound showed that all the bonds in the cyclic structure of benzene are equal. This also implied that since the carbon-carbon bond lengths in benzene are equal, then there are the same number of electrons between the carbons that make up the cyclic structure. To account for this strange feature, chemists then proposed that the pi electrons, which are the electrons of the double bond in benzene, are delocalized. They are spread out over the entire carbon atoms of benzene. This accurate structure in which the electrons making up the double bonds in benzene are constantly moving amongst the carbon atoms and are not restricted or localized between any two carbon atoms is called the resonance structure of benzene. The resonance structure of benzene can be represented by a hexagon with a ring inside it and hydrogen atoms sticking out of the vertices of the hexagon. Each carbon atom is represented by a corner of the six-sided hexagon, and the internal ring represents the delocalized pi electrons. The hydrogen atoms may or may not be shown, but when they are not shown, they are implied. So, if you draw the resonance structure of benzene with or without the hydrogen atoms, you are right. Benzene has several important uses. It is used to make other aromatic compounds, which have several applications in plastic making, drug production, and as solvents. Benzene is also found in crude oil. In this lesson, you have learned that benzene, the parent compound for many other aromatic compounds, has a resonance cyclic structure in which its pi electrons are delocalized all over its 6 carbon atoms. Soon, we will learn about other compounds derived from benzene.